about ladder functions for classical and quantum exactly solvable systems. So please, Vero.
So thank you very much for the invitation to talk here. I've been, I think it's my fourth Quantum Fest, but I've been visiting Mexico and CinvestavIPN many times, and I have a lot. I have my collaborators, and I have now recently collaborate with some of the students of my old collaborators, I must say. So I will speak about ladder functions or operators. I must mention that this is a work which is not in collaboration of my Mexican colleagues, but it is in collaboration with some people I know for a long time in Valladolid. And in fact, Sengül is in Ankara, but she's visiting so much Valladolid that she's almost part of the team of the Valladolid team. And Lugar is my master student. So I must say that I just put the outline, but I want to say that the idea to do this work was based on some observation I've made. I've been working for a long time on coherent states, and in particular as a definition of coherent state as eigenstate of an annihilation operator, which is a special ladder operator. And then I realized in working in one-dimensional quantum theory, that all the ladders in much of the ladder operator in the solvable system were represented as a differential operator of order 1, but at the price most of the time to involve as well the number operator. And at the same time, I discovered a work from Sengül and Javier, where they were dealing with the classical counterpart of ladder functions. And they were revising or classifying as well the ladder function in terms linear in the P, in the momentum, and depending on the Hamiltonian as well. So I thought this classification was complete, but I realized by dealing with a new system here, which is the Rosen-Morse system, that this classification at the classical level was not complete. Okay? So we decided to address the question, and as well, when I was trying to find the ladder operators in the quantum system, I did not succeed. Okay? So I will develop a bit all these ideas. So first, I will give a short review of the theory. The theory of ladder operators. I will construct the classical function, and I will as well construct the quantum ladder operator. But my main point will be really to take the example of the Rosen-Morse system. So, you know very well, oops, sorry, that if I come back to the quantum mechanics, the one-dimensional quantum mechanics, ladder operators are defined as operators connecting eigenspace of a given operator, which is essentially the Hamiltonian. Okay? And then we can, using the ladder operator, obtain the spectrum, partially or completely. And as well, we can define with this ladder operator, which we call A and A dag, or A plus and A minus, and together with H, we get what we call a generalized Heisenberg algebra. Okay? And we can add as well all the constants of motion in order to have the spectrum generating algebra. At the classical level, analog objects could be defined, and they have been defined more recently in a way, and they lead to similar algebraic structure. We will see in detail what's happening. And then instead of operator, we have function. So we call them ladder function. And then at the classical level, we can as well use this construction to determine the motion of the system and its frequency. Okay? So we start with the quantum mechanics formalism. So as I said before, we have the ladder operator, A plus and A minus, and then we define them as the action on the energy eigenstates. So we know the spectrum of the Hamiltonian, we know the eigenvalue, and when we define the annihilation and creation operator, we pass from psi n to psi n plus 1, and psi n to psi n minus 1. And more explicitly, we can introduce this function here, which is a function of n, and which does the connection, right? This function is not defined uniquely, okay? But it's essentially the definition. And using that, we can see some properties, like here, acting with h on these states, we get here this relation as well. We get it clearly an eigenstate of h. More than that, we can write the things this way. So usually, the most general form is this form. So we have the commutator of the h and a plus and minus, which give h up to a function of h, of the Hamiltonian, which is diagonal. This function is diagonal with respect to the action on psi n. Okay? And we have also what we call the factorization here of the product A plus A minus. In some very simple case, like the harmonic oscillator, we know that we factorize the Hamiltonian, but most of the time we factorize a function of the Hamiltonian. That's what is written here. So I go quickly here. That's what's written here. And so to get, we have what we call the generating Heisenberg algebra, using the commutator of h and a plus a minus and this relation. But keep in mind that we have as well the factorization here. Okay. So this is the main context for the quantum case. For the classical case, we use the Hamiltonian formulation, and we will define again such a structure, the generalized Heisenberg algebra, a bit the same way. So we extract from H and from some definition of A plus A minus, but here we have some function. I don't say what is the type, what is the form, exact form of the function, but we use this as a definition of the annihilation and creation operators. And we can see that with this definition, we have as well a factorization at A plus A minus of which is a function of h. And I decided to use the same notation here. And we have a relation between beta and alpha and k. And then in order to define the motion, we know that using this ladder function, we can determine some constant of motion, which are called q plus and minus. And then we can extract, with the eigenvalue here, we can extract the motion, the time-dependent fast space of the system. Now, for most of the non-solvable systems, that's what I say to you, it has been shown in the work of Sengul and Javier that we can explicit the formula for the ladder function. So we assume that the ladder function takes this form. And you see what I said at the beginning. Well, we call it a factor function, a factor function is defined this way. So what you see is linear in P, and we have a dependence in X, evidently, but we could have a dependence in H or in the energy. Right? I use H instead of E, energy. Okay? So what I did not say, is what I say here. In the following, we will have to combine this factor function. So I'm cautious because I don't know if these are the proper physical ladder function. No? So the reason why I introduced these functions. And to do this, we will need to keep a way to keep track of the contribution of the factor functions. So I say to you that, for example, if I take two functions, f and g, such that they factorize. So we use f star here because we have only the conjugate here. And then if we do that, we can replace the bracket here, divided by f, by a certain function lambda f. And using the property of the Poisson bracket, we can see that the contribution, what I call contribution, of the product of two functions is essentially the sum of the contributions of the two functions. So it means that I will probably work with not only f, but more than one function. So now if I do that, I can use my definition to write the contribution of the A plus and A minus, my ladder function, right? which is associated to ideally to the frequency of the system. Okay? So what I say is that it's not only fj that I will do, but possibly I will make more products function to get essentially this ladder where alpha would be exactly the frequency of the system. As I said to you, for most of the solvable system, we have an explicit formula for the ladder function. So these are the cases where we have a function linear in P, where, in fact, as I said before, it's not only a function of x and p, but it's a function of x, p, and h. Okay? And the dependence in h will be explicit, except possibly the introduction of an arbitrary function here. Okay? So most of the time, and it's special here, most of the time you see that if you extract the dependence in h, in front of p you have a separation of variable, essentially, but not in a, right? And they will satisfy essentially h equal p squared plus v. Okay, potential. I take an example. I don't want to go through all the examples. As I said to you, the classification has been done by Cruz and Negro, but I try to take an explicit example because it's quite easy related. Is quite related to the one I will have problem with, in fact. So this is the hyperbolic Peuchat-Taylor potential. You can do that with the trigonometric, you can do that for the Morse potential, you can do that for many potentials. So if you take the Hamiltonian, you know the Hamiltonian is on this form, and if I look at the ladder function in this region where the energy is negative, so that the motion is bounded and periodic, you get this form. So you see, this is a nice form. First, this is the B I have introduced before, okay? Because it's a coefficient of P, linear in P. A plus and minus are linear in P. And you have here the A, which depends explicitly in X, but in H as well, okay? And the square of minus H is clearly reasonable because my energy are negative, right? So, and you get the frequency. So it's one of the simple cases we can find in the classification of ladder function for solvable system. Now I come to the case of the Rosenmos potential. again, this is the hyperbolic case. You see, the complication comes from the term, the extra term here, which is a constant multiplied by the hyperbolic tangent, right? And then we have some constraints, some condition for the shape of the potential, and we have as well the energy, which is less than minus beta, and the energy is negative. Now, this is the Rosenmos potential, for an example, right? And it's in quantum mechanics, it's perfectly solvable as well. Okay. And now, the idea was, as I said to you, we were trying first to find a linear function, okay, a factor function, but by chance. And it was not only by chance, it's also because we knew what we get for the Peschel-Teller, so we tried to generalize the Peschel-Teller case. So we said, okay, we start with some function, and we notice that we have an extra dependence here in epsilon, so we can choose a plus and minus sign, and then we get something like that, which is nice, because b of x is still Cosh, and the A is B multiplied by this quantity. If you look at the Peschel-Teller, the Peschel-Teller, you see the expression here. It's quite similar. So we were thinking, oh, it will be an easy generalization, but no. But finally, we have first something. Yeah, we have our factor function. It factorizes this way. We have some function here, which are a bit complicated, but it is easy to write. And then, so it was our guess. I mean, to my student and myself. And this was the guess of my colleague, because they were treating the Kepler-Coulomb potential, and they found another factor function. So, and then when we saw that there is a link between them, we discovered that there is another factor function, two, in fact. As you see, and you see now, instead of Cosh, you have this quantity here, and you have a bit more complicated form, but always the same dependence in x, but the extra term are a bit more complicated, and it satisfies the condition here. Okay, so we have a bunch of functions we can deal with, and with hope, we possibly get something which will be the ladder function, the physical one, related with the frequency. So the first thing I want to say, and we found it, must say, after publishing the work with Javier and Sengul on the classical case, that in fact the function, and I give the example J1, right? In fact, the function there, which seems to be very complicated, yeah? And new, is not so new. Oops. It is. It can be written as a product of f-1 and f1. You see, I had epsilon there. Okay, and then my function here. You see what they are. Okay, the usual one with an extra term here because of the presence of b. Okay, so I do that because you will see later. And we discovered it when we were trying to generalize the classical case to the quantum case. Okay? Now, the important thing is what I mentioned before. I spoke about contribution. You know, this lambda. And by chance, I mean, we calculate that. And you see that they're very similar, right? So the contribution here is dependent on x and on tan x, but you know that the contribution of a plus a minus, because it's associated with the bracket of a plus and a minus, the contribution must be independent on x. So that's easy to realize that we have to make a product, a certain product of these functions, such that we eliminate the dependence in X. Unfortunately, the dependence in X is the same. And then we chose this function. So we had a lot of choices. We have different reasons, and it's too complicated, and I have no time to explain everything. But what we found, it's not a product of two functions, because now we have a factor, an exponent here, right? So we have a function of h, but essentially this will give the ladder operator. Okay, right? Okay, and then what I want to say is that now you take the limit when b tends to 0, you find clearly what you had before. Okay, so it's nice, and it's up to a factor dependent on h. So it's fine, and then we can go forward. Okay, we solved the classical case. Now we want to go to the quantum case, but I mentioned here, well, there's a big equation, but I mentioned that having the annihilation operator, we can find the constant of motion, and we can solve the problem and get the motion, the evolution in time of the x. Okay? Now I have everything, and it took a while, and it's only recently, and the work is in progress, that we found a way to relate that. Okay? Because as I said to you, perhaps the first thing was to use direct computation to try to find the ladder operator in the quantum system, right? So what I mean for that, I say I have a quantum system, a one-dimensional quantum system, which is solvable, and I define an annihilation operator as acting on the space, the eigenspace, okay? And the eigenfunction are labeled by n, right? And as I said before, the price to pay in general is to add a dependence in n, which is clearly the eigenvalue of the number operator. So after I find a general form for this a minus small n x, I can make it an operator depending on x and the derivative in the np, essentially. Okay? So I say here, the idea is to start with n equal 0, 1, 2, clearly, and to find an expression for n. So we assume that it takes the form, this form, right? And we introduce the number operator. It's just what I said. Okay? And again, if you look at the construction of the creation of the operator, we can always get the factorization here for a function of the Hamiltonian, right? So, oops. So let me illustrate first the case where it works easily. So this is the infinite well. I decided to take another one just for having another example. The infinite well, we know the spectrum very well, and you see the eigenfunction are very simple. The energy is proportional to n squared, and then we get the definition here. Well, here I have fixed the Kn as simple as possible, like the harmonic oscillator case. But as I said to you, they're not unique, so you can change the function here. But usually you have the way to change it by multiplying the ladder, the original one, by a certain function of n, right? But what you see here is what I mentioned before for the partial Taylor potential. In fact, yeah, in the quantum case, you have the dependence in the first derivative in x. You have the function sign here, and then you have n cos. Okay, so you see the nice form that you recover for most of the solvable potential. So this is one of the simple example. So now my aim is that is to generalize for the Rosenhaus potential. Here I took the form we used to take. Instead of taking C here, I take B0, B0 minus 1. And we have this, this potential, which is a realistic model for studying vibration of polyatomic molecule. Okay? So we have this kind of potential. We know the spectrum. I want to mention that the spectrum is given is negative, the energy are negative. You see the part which corresponds to the partial Taylor potential, which is B0 minus n squared, and the part which is associated with the extra term involving B, big B. Okay. We know the eigenfunctions. They are hypergeometric function in terms of this quantity. And then you have on these quantities where you see here the complication here, using recurrence relation, for example, comes from here. We have a dependence which is not linear in any here. Right? So we have everything. We know what's happening for the partial Taylor. Now I'm in the quantum case. So you see that instead of having square root of minus h earlier, in the case of the classical case, I replace here by b0 minus 1 minus n ksd, which is essentially the square root of the energy, okay? Minus the energy. So that's what we have for a start, okay? And just remember that, well, I like this term because I hope to get extra term if involving big P. Now, as I said before, naively, we start trying to compute A0, A1, and you easily get the expression. And it looks nice because you see, if you put n equal to 0, you recover the partial Taylor case, and it seems that it's very nice because it's constant, and it's depending on big P, but B0. Yeah. And more than that, you look at A1 minus 1, and accept the term which is here, the exponential, you find again the cosh, the derivative, and also the term, the additional term. But it stops there. It doesn't work anymore when you go further. So the idea was to exploit what we have done before in the classical case. As I said to you, we have to pay the price to increase the number of functions we want to put in the annihilation, proper annihilation function. So in the case of the quantum case, we have been working very close to what we have done in this classical case. So as I said to you, we replaced here b0 minus n, well, it was the square root of minus h, you remember? But here we have an extra term, and let me say now, introduce another dependence in k, right? Where the term seems to look like we had before, like here, except that it was the same. And the problem with my naive way was to take k equal n, and it was not working. Okay? So now what I say is that we take these two functions. Let me say that it's very nice, a nice process, because when you get that, it's so close to what we knew before, and then what we think we have to do is to make some product. But which product we have to do, right? So look at first the case I have already solved. Easy, it's f0, 0 minus, and this one up to the exponential factor is f11. Okay. Now I have computed using Mathematica, but my student Luca used the connection, the comparison with the classical case, and I have checked the results he gave to me. And now I can tell you that this is my A2, and we start doing the computation. So I look at it. What is it? So A2x. So A2 minus A2 minus 2 act on psi 2 to give something proportional to psi 1, right? But don't forget that my psi n depend on x, b0, and b, the big B, right? So now we try to construct this operator as a product of, again, this factor operator, which are quite simple, right? We start with 2, 2. Here we have 1, 2. And here we have 0, 1. Do I remember that it's n and k in my definition. And now I have another one. And now you can admit that I have such a generalization written in small n for the time being. Yeah. So in order for you to see what I'm doing, we have this scheme. So the idea was to start with what I call HB. B0 is always the same, but it's big B, which will change. So I start with my Hamiltonian, original Hamiltonian, and I know that I want to act with A2 minus to go to the psi 1 of the original Hamiltonian. What's happening? So when you look at the F22 minus here, instead of going to the state phi 1 here, which you know it doesn't work because we tried, you go to another phi 1. And the phi 1 corresponds to the Hamiltonian, which is where you have changed B by this expression. So you have essentially a phi 1 for the new potential where you have replaced B by this expression. Now if you continue, so that's nice because the first parameter, which is n, lower in the text. The next one, the 2, the k, goes to that. And so on. So here, now, you have F1, 2, so now you lower 1 to 0. And then, but psi 0 doesn't belong to H1, HB, it belongs to this Hamiltonian. And then, you know, you have in mind that you want to recover the original psi 1 for B. So you have the price is to use this exponential, which doesn't change the number state, but it changed the B. And it changed it the way that when you go now with F plus, you reach psi 1. It's clever. My student had problems to explain that to me. And so that's very nice. I mean, and you could say, okay, I make some comment. Okay, you have a bunch of products, so it's not anymore a first order operator, a differential operator, but you know that you work with your Hamiltonian, so you can replace all the second derivative by the potential minus the energy. So it becomes very complicated. I understand that there's a lot of multiple of the B0 and so on, but essentially it works. And you have here the expression I gave as well for A plus, which act the same way. I want to make a comment for the limit. I did not put any other slide here for the limit for B equal to 0, but I think I can show you. Okay, I can show you. I don't remember. Perhaps I can show you the expression of. Okay. You see, when, for example, for the A2, for B equal to 0, all these Fnk become Fn because there's no term here. And what we do, in fact, here, what we do here, we need only this one. I mean, that's clear, because it doesn't depend on B. It doesn't change here. And so we go immediately with the F22 minus to psi1, the good one. And the other quantity are multiple. We multiply by some constants. Okay, so that's nice as well that we recover the case, the limit for b tends to 0. Now, my last comment is where does it come from? I mean, it comes from somewhere, this process, and I will be short because we still progress to make it very, very clear, I think. But essentially, I want to make the connection with the classical case, because as I said to you, we decided to construct this ladder operator. I chose the annihilation operator as a product of different factor functions. We have recently observed that the factor that we have here, the exponent, is simply written like that. Okay, it was a more complicated form before, and as I said to you before, J1 minus is as well a product of two function f. So in fact, the J, which was so nice, it's essentially the product of two f. So it's very nice. So we have more product here, and then what I say here is that if I write what I just said, we have essentially, I have to take into account here this quantity, but essentially up to a multiple of the function of h, you have f1 minus here, and you have f minus plus with the exponent here. Now, let me think of the quantum case. You remember, I don't think I reproduced the thing. If you remember, when we deal with the first one, it was the one which I call in the other slide the F22, the F22, the F33, you see? And this one is, because of the definition, is the one with k equal to n. And it corresponds to the case where here you have the expression in the classical case. I said to you, this is the square root of the minus h, minus a, and it looks to the case where we have, in the classical case, we have, in fact, transformed the phi, the classical quantity, to the quantum one here, right? So it's natural, and it's natural to say, for example, so you have here this expression, you derive it in the classical case, but if you now you go to the quantum case, if you replace phi 1 by b0 minus n, you find essentially phi minus 1, which is b0 divided by 2b0 minus n. This is the connection with the classical case. And now, as I said to you, look at the quantum case. The product here is given here, and what I have said here is the way to go from the classical function to the quantum operator is, in short, to promote f minus 1, so the last one, the f minus and f minus 1 function to an operator, which is this one, and to promote these, all the other quantities, all the other product, to the to promote this product, this function, to the operator here. Okay, and then so we have to explain a bit more in detail how we do, but essentially this is the result. Okay, and as I said to you, I explain here why phi 1 classical is becoming b0 minus n, and phi minus 1h is becoming 2b0 minus n. But you know, we can have the freedom in the quantum case to put k here. Okay. Right. I'm almost finished. I said to you the nice thing here is to see that the complicated ladder, if I try to reduce the order with a third differential operator, it becomes very horrible. But if you look at it as a product of functions, it looks very simple because the functions are essentially this first order differential operator. You have another way to produce some factorization, and you know that using the supersymmetry. And then if you look at the Hamiltonian, I want to try to make a connection, but I have not succeeded in this complicated case. But I want still to mention it because I think it's something interesting in here. You remember that when you take a Hamiltonian, you can factorize easily the Hamiltonian, but unfortunately, except for the harmonic oscillator, the W here, the x minus and x plus, are not annihilation and creation operators. And we call this function the superpotential. Okay? So these are not ladder operators. But if you look at the hierarchy of Hamiltonian you can construct using supersymmetry, I want to say, if you start with x, it's not a plus here, the plus is not, no? If you start with the Hamiltonian H1, okay, H1 here, okay, okay, I know it. You can construct H2, which is, sorry for that, which is the contrary, okay? It's x minus x plus, okay? And you have a new Hamiltonian, and then after continuing the process, you can produce another Hamiltonian with an x2 here, h3, and so on, until hn. And to do it in short, I give you, at the step number n, what will be the function wn in my superpotential, right? Which is a linear operator, a differential operator of order 1. And look at it. So it looks very similar to the function I have defined before. A special one because the n is here, n minus 1 here, and n minus 1 here. So it's the same n and k, okay? But it's very similar, except that we don't see the cosh, okay? So the cosh is not there. So, but if you multiply by cosh here, you recover our functions, okay? So I have not been able yet to make the connection, but it seems to have something to deal with. In the case of Peugeot-Teller of the infinite well, you have a very nice relation, but not here. And what you have here, I can give you the new potential here. But what you see is that it's shape invariant in the term of the Peugeot-Teller potential, but doesn't change B. And something can be done, I think, because what I say to you is that doing this supersymmetric process, I change B0, but I don't change B. Instead, in my other case, I was changing B. Okay, and to finish, to complete the discussion, what I said before to you, we had the idea of these things because Javier and Sengul were working on the Kepler-Coulomb potential, but we can make a connection with this system. That is the reason why I consider only the Rosenmos potential, because it could be nice to see the expression in the case of the Coulomb Kepler-Coulomb system, but it will be easy to make the connection. And my last transparency is to give you some of the references of the main paper. We have been consulted, and thank you very much for your attention.
Okay, we have enough time for questions. Comments, please.
Yes, I wonder about in the quantum case, how this nice product, if you could say something about the mathematical physics.
No, not yet, but it's it's a good question. I have no time to look at it. So you speak about on these F plus and F minus and K. I've not yet done that, but it would be nice to do that.
In the case of the classical systems, those ladder functions were constructed for the bound regime of motion,
Yep.
or they can be also used
That's for the bounded regime, not for the other one.
for the static analysis.
No. No, I don't know how to do it. You have some ideas?
More questions?
Right. Where in your process you are working like in the opposite direction. You have a quantum system and you obtain the classical system. In the quantum system you can construct coherent states.
Yeah.
What will be the analog of those coherent states in the classical system?
I don't know. I don't know. That's an interesting question. I have not seen anything about coherent state in the classical system.
Oh yes,
Yeah,
there
there's
are
something.
some formulations of coherent states in the classical picture, but it is not clear. I mean that coherent states are quantum, of course, with a global behavior like a classical state. And in the classical picture, all the states are already classical.
Yeah,
So
yeah.
that you have at most the connection with some uncertainties, which are very close to the quantum ones. And in this sense, you can introduce the notion of coherent states connected with this. Yeah. But they are already classical, so that.
I think that maybe if we know something about the algebraic properties, we can find coherent states in the group theory kind of, but in the case of coherent states being other states of the annihilation operator in the classical case seems a bit strange. Obtain something like that because the ladder are functions, not operators.
Mm-hmm.
Bernardo, please.
Well, maybe it's a very wide question. You see, you have systems where wave functions are bound by two states or by three states. Now, we know, and you also have continuous systems and discrete systems. So, I mean, can you have coherent states in all of these cases? Where you have two-term recurrence relations, three-term recurrence relations. And recurrence can be continuous or discrete.
Yeah.
If you can.
Well, we have been able to construct the coherent state for the discrete one. We have not done for the Rosen-Moss, for example. But when we consider the coherent state for the Rosen-Moss potential, we did not need to have a differential radialization. We only need to have the definition with the annihilation operator. Right? Eigenstate of the annihilation operator. We suppose that it exists. Now we show that it exists in a way. But as Sarah said, there is other definition, group theoretical definition. And I don't know, I mean, with the final A, I know the relation, because it's my generating general Heisenberg algebra. And as I said before, I can use the Kn in a way that it closes an algebra, for example, like the oscillator algebra. But I can choose as well the Kn such that it factorizes the Hamiltonian theory. But I don't know how can relate this to the structure of the F. And for the continuous one, I don't know anything.
Okay, more questions? Please.
Thank you very much for your talk. I wonder if in your transition from classical to quantum and back, there are some signs of fractality.
Yeah, possibly. That's what I say. I hide a bit. What is it inside the new quantity, new H, which is the quotient of psi phi minus 1. And that's what I say to you. It's still to be investigated, the connection. So that's easy. I mean, what I say to you, my results in the classical case are correct using this function and this one for an annihilation operator, right? And my construction is correct here. It does the job. The problem is, in fact, to make it new H and understand what is how it is related. This one, yeah? You know, because if I say I promote this one to that one, it's not so easy to say this is a product of the same one, okay? But it's not true because I have a product of different ones here. So that's the reason why I say I hide a bit. Well, I did not hide, but I say to you, we have not really finalized the connection. Okay? But we know that the results are correct. It's the passage, the way to go from the classical to the quantum case. And as I say to you, the quantum case, the use of this product were inspired, not completely the same, because we have to introduce the n, the dependence in n, the number. And the problem came at the beginning by the fact that the spectrum, when, for example, I just try to go back to the spectrum of the Rosenhaus potential in the quantum case. Yeah, you see, when I have the energy here, okay, if I don't have this term, no rational term in n, the passage from the classical to the quantum is easy because this is the energy. But myself, I'm in the quantum theory, I use n instead of h, okay? But I can inverse. I mean, I can express h, a in terms of n, or n in terms of a. The problem is that how to inverse the dependence here, because from a classical case, this is h, okay? That's the point. And that's where it was, it took so much time to get the connection with the classical case. Okay?
Okay, I have a question and a comment. It seems to me that the action of this ladder operator you have constructed produces the transition from one member of a given family to another one, and then arriving to the original member of the family. How do you think about this, all this change? It seems to me that all these different expressions for age are different elements of a given family. And you are departing from a given member and arriving to this member. This is very tricky to me because this is new, of course, in supersymmetric quantum mechanics. But have you discussed this with Lizzie?
No, not yet. No, not yet. And no, I understand what you are saying. And in fact, perhaps here as well, we must investigate much more what does all these function in general.
Yeah. I wonder if it is possible to find a general expression that involves all these Hamiltonians as a given function. That's the point. As it is usual in the supersymmetric transformations.
Okay.
I don't know. No? And the comment.
You mean two parametric Hamiltonian, one multiplicative and the other one?
Yeah, but this one, in this case, for the Suzy case, of well, perhaps it's because I choose always the ground state, the new ground state. in my supersymmetric transformation for going from H1 to Hn. That's the reason why Wn does not produce the change of big B. Okay.
Yeah, I think that if you take another state, for instance, Cn, in order to arrive to Cn minus 1, you will obtain the same chain of communities. So that it seems that all of them are different members of the same family, and you are moving between the members of the given family, which is not already reported in this perspective. And my comment is that this function cost that you have to introduce as a factor of the conventional operators in order to obtain not the factorization operators, but the ladder operators. We have some reported about this with Luis B. and Javier, and we call this refined factorization.
Okay.
Because the key is that you can show that if you multiply by a general function the factorization operator, this indeed makes no change in the factorization. But this produces very nice properties from the mathematical point of view, considering these operators. And I think that this is also at least.
Yeah, you send me the reference.
Yeah.
Okay.
So if there is no more comments, let's say again, Professor Bogdan.